Leibniz's notation for calculus. Now, Gottfried Wilhelm Leibniz developed calculus in Germany independently of Sir Isaac Newton in England. The notation he developed is the most commonly used, although we still do use Newton's notation as well. Now, he used delta x to mean a small increase in x and delta y to mean a small increase in y. To find the gradient function of y equals function of x, we choose 2 points on the curve, P with coordinates x, y, and Q with coordinates x plus delta x, y plus delta y. We then draw a triangle under the line. Going from P to Q, x increases from x to x plus delta x, so the base of the triangle is delta x. Y increases from y to y plus delta y, and so the height of the triangle is delta y, which means the gradient of PQ is delta y by delta x. Now, if we move the point Q closer and closer to P, then the line gets closer and closer to the tangent at P. Delta x and delta y will both get closer and closer to 0. However, the fraction delta x over delta y will remain large and will get closer and closer to the gradient at P. Now, Leibniz used dy by dx as the gradient function. So dy by dx is the gradient of the curve at P. So dy by dx is the limiting value of delta x over delta y, as delta x and delta y both tend to 0. So he wrote dy by dx is equal to the limit, as delta x tends to 0, of delta y over delta x. Dy by dx is called the differential of y with respect to x and is in fact the gradient function. Differential by first principles. Now we have a result. Given that y is equal to function of x, then dy by dx is equal to the limit, as delta x tends to 0, of the function of x plus delta x minus the function of x all over delta x. Now we can use this to find the differential of any function. In practice we don't use it very often because we don't have very many completely new functions. We would use it, for example, to find the differential of trig functions. Now, to show that it's true, we choose 2 points on the curve, P with coordinates x, y, and Q with coordinates x plus delta x, y plus delta y, and the gradient of PQ we have shown is delta y over delta x, or we could write that as y plus delta y minus y over x plus delta x minus x. But y is the function of x, and y plus delta y is the function of x plus delta x. So substituting those in the equation above, we have delta y over delta x is equal to the function of x plus delta x minus the function of x all over delta x. But dy by dx is equal to the limit of delta y over delta x, as both delta x and delta y tend to 0. And so we have the result, dy by dx is equal to the limit, as delta x tends to 0, of the function of x plus delta x minus function of x all over delta x. So let's see how we would use this in a practical problem. Suppose we want to differentiate y equals x cubed using first principles. Now we can draw a diagram of that. We can mark in the points, we can draw the line, but we're going to use the formula dy by dx is equal to the limit, as delta x tends to 0, of function of x plus delta x minus function of x all over delta x. Now, function of x plus delta x is x plus delta x cubed. So we have dy by dx is the limit, as delta x tends to 0, of x plus delta x all cubed minus x cubed all over delta x. And we can expand that cubic bracket. And this gives us on the top x cubed plus 3x squared delta x plus 3x into delta x squared plus delta x cubed minus x cubed all over delta x. And the x cubes at the front and the back cancel out. So we're left with dy by dx is the limit as delta x tends to 0 of 3x squared delta x plus 3x delta x squared plus delta x cubed all over delta x. And if we divide the top all the way through by delta x, this leaves us dy by dx is the limit as delta x tends to 0 of 3x squared plus 3x delta x plus delta x squared. Now, if delta x is tending to 0, then all the terms which are multiples of delta x will also go to 0. So the only term we're left with is dy by dx is 3x squared. Let's look at a similar example that is a bit harder. Differentiate y equals x to the n by first principles. Now again, we can draw a diagram with points P and Q and the line joining them up, but we're basically going to use the formula dy by dx equals the limit as delta x tends to 0 of the function of x plus delta x minus the function of x all over delta x. But using the function y equals x to the power n, we have dy by dx is the limit as delta x tends to 0 of x plus delta x to the power n minus x to the n all over delta x. Now we can expand the bracket using the binomial expansion. X plus delta x to the n is equal to x to the power n plus n x to the power n minus 1 delta x plus n into n minus 1 x to the power n minus 2 delta x squared plus n into n minus 1 into n minus 2 x to the n minus 3 delta x to the power 3 and more terms. Now that means dy by dx is the limit of that minus x to the power n all over delta x. And the two terms at the front and the back, x to the power n, both cancel with each other. And so we're left with dy by dx is equal to the limit as delta x tends to 0 of n x to the power n minus 1 delta x plus n into n minus 1 x to the power n minus 2 delta x squared plus more terms involving powers of delta x all over delta x. If we divide all the way through by delta x, this leaves us with dy by dx is the limit as delta x tends to 0 of n x to the power n minus 1 plus n into n minus 1 x to the power n minus 2 delta x plus more terms with powers of delta x in them. But as delta x tends to 0, all those terms which are multiples of delta x will also tend to 0, and so we're left with dy by dx equals n x to the power n minus 1. So if we have a function y equals x to the power n, when we differentiate it, we multiply the term by n and reduce the power of the term by 1. This is known as Wallace's rule, and we will be using it a lot.